Hello, ladies and gentlemen. Let's continue on with the mass balance today. So last time in the previous lecture, we applied the Reynolds transport theorem for beta equals mass, and we derived conservation of mass for an open system. So let's do an example or two today involving application of the mass balance. And let's see if we can figure out how to do these sorts of problems involving mass balance on open systems. So topics today: open systems. We're going to deal with the mass balance, see what kind of information that yields us on problems and on situations, and we'll do a couple of examples. Okay, so let's look at what we're going to do today. Let's do an example here. What we have is a duct in which air flows in on the right and out on the left. Now, this duct contains a heating element. So this heating element is dissipating electric work in the form of heat into this air duct. And so the air, as it flows in from the left, passes over the heating element and flows out on the right. Enters on the right, passes over the heating element and flows out on the left, gets heated. So if the inlet is location 1 and the outlet is location 2, the air gets heated, so T2 is greater than T1. Now, if we assume that this is a constant pressure situation, so the pressure at the inlet and the outlet is the same, then we can say that density goes down as we heat the air. As an ideal gas or a gas gets heated, density tends to go down. As a gas is cooled, density tends to go up. So we have some numbers here. The density on the right, the inlet, is 1.2 kilograms per cubic meter. And the density on the left, where it is heated, is 1.05 kilograms per cubic meter. So density goes down as temperature goes up and the air is heated in this duct. Now, what are we supposed to find here? The air flows in at a certain velocity. So we have an area for the duct. So the velocity on the right is VEL1, and the velocity on the left is VEL2. So I want to know what the ratio is of the outlet to the inlet velocity. As the air heats up, becomes less dense, presumably the volume flow rate goes up and the velocity goes up. Hopefully the air is coming out at a higher velocity than at the inlet because density is going down. And you'll see this in just a minute. Okay, so heated flow in a duct. T2 is greater than T1. Density falls as we go from the right to the left-hand side of the duct as it is heated. We're supposed to find the ratio of the outlet to the inlet velocity, VEL2 divided by VEL1. That's what we're supposed to find. Now, assumptions here. I'm going to assume everything is constant in time, steady flow, steady state. And I'm also going to assume that the flow areas, or the area of the duct, is constant. So A is equal to a constant. So those are my assumptions in this problem. Okay, let's apply conservation of mass. Let's get to the analysis here. Apply conservation of mass and see if that can yield us a ratio of velocities between the inlet and the outlet of the duct. So analysis. So let's write down conservation of mass. So mass conservation. By the way, let me draw my system here. The dashed line here is my control volume. So this dashed line, is the control volume, or if you like, CV. It's my control volume on my system. It's clearly an open system because we have an inlet at location 1 and an outlet at location 2 in which mass passes across the system boundary. This is not a closed system. This is an open system. So We can apply conservation of mass to this open system and see what we get. Let's see here, mass conservation. So we have the time rate of change within the control volume is equal to the sum of the mass flow in minus the sum of all the mass flow out. Okay? We may have multiple inlets, multiple outlets. That's what the summation signs are for. Now, steady state, steady flow. Nothing varies in time. Steady state means the amount of mass is not changing within the control volume. So there's a certain amount of mass inside my duct. It's not going up or it's not going down. That's what steady state refers to. No changes with respect to time. So dmCv/dt, change of mass within the control volume with respect to time, is 0. Why? Because this is steady state. So that term is 0. Now, how many inlets do we have and how many outlets do we have? Let's go back to our control volume and figure out what these summation terms are. I have one inlet at location 1 and one outlet at location 2. So I'm going to put in m.1 and m.2 for my inlet and outlets. So my inlet is at location 1, so I have m.1. I have one inlet at location 1, and I have one outlet at location 2. So this implies 0 is equal to m.1 minus m.2. That's what mass balance says. Let me take the m.2 term and put it over on the other side of the equation. What does this imply? m.2 is equal to m.1. The mass flow out is equal to the mass flow in. m.2 is equal to m.1. Outflow equal inflow. Outflow equal inflow. Pretty intuitively clear. What flows into the duct? What flows into the duct at the inlet at location 1 must flow out at the outlet at location 2. That's all that mass balance says in steady state. Inflow has to equal outflow. Pretty simple so far. Okay, let's calculate. Let's actually write an expression here for these m dots. So m.2, the outflow, what's that equal to? Well, the outflow is equal to the density at the outlet times the velocity times the flow area. So there's some kind of flow area, okay? And we're actually assuming that this flow area is constant because the duct is assumed to be constant area. So m.2 is equal to the density at location 2 times the velocity at location 2 times the flow area at location 2, which is equal to the flow area A flow. We're assuming it's all the same. Same thing for m.1. The inlet flow, mass flow rate, that's equal to the density at the inlet times the velocity at the inlet times the flow area, which is constant throughout the duct. Let's make the substitution here into our mass balance. So we get rho 2, velocity 2, area flow equals rho 1, velocity 1, area flow. Notice the flow areas are the same, they cancel out. We're assuming that this is a constant area duct. And I get outlet density times the outlet velocity is equal to the inlet density times the inlet velocity into the duct, all right? Let's solve for the ratio VEL2 over VEL1, which is what we want. Velocity at the outlet divided by velocity at the inlet is equal to density at the inlet divided by density at the outlet. So the ratio between the inlet to the outlet velocity is equal to the inverse of the ratio of the densities. So what that says is, my inlet density is highest and the outlet density is lowest. That means my outlet velocity is going to be high and my inlet velocity is going to be lower. Okay? Let's plug in some numbers here. Let's see, inlet and outlet velocity, 1.2 and 1.05 kilograms per cubic meter. 1.2 kilograms per cubic meter, 1.05 kilograms per cubic meter. Kilograms per cubic meter cancel out, and we get a dimensionless number. Velocity out over velocity in is dimensionless, so we better get a dimensionless number. Let's see here, 1.2 divided by 1.05. 1.14 is the ratio of the outlet to the inlet velocity. VEL out over VEL1 is 1.14. Okay, so basically the outlet velocity is 14% higher than the inlet velocity. The outlet velocity is 14% higher than the inlet velocity. Okay, pretty simple problem. Steady state problem, application of the mass balance. Pretty simple problem. Let's do another problem here. Let me pause it here for a minute. We'll get another problem set up. All right, let's go after a second problem here. What we have is a water tank. So here's our water tank. It's a circular water tank and it's got a drain at the very bottom. Now, initially at time t1 or 0 seconds, t1 equals 0 seconds, the height of water, H2O in the water tank, is equal to H1, or if you like, 1 meter. So originally, we have a depth of 1 meter of water in this water tank. Okay, and it's a circular tank. The cross-section area of the top of the tank is equal to A tank. So it's a circular tank. The top cross-section area is A tank, and that's equal to 2 square meters. So it's a 2 square meter area tank with a height H. Now, the flow out of the bottom drain, and it's a circular drain out the bottom, the flow out the bottom is equal to the flow area, A out. So this is a circular pipe coming out the bottom, and it has a certain flow area. The mass flow rate out the bottom is equal to the flow area for the outlet times the velocity at the outlet times the density of the water. So we have flow going out of this bottom drain, and the bottom drain has a certain cross-section area and a certain flow rate or flow velocity, VEL out. The outlet velocity through the drain is proportional to the square root of the height of water in the tank. The more water there is in the tank, the more flows out the bottom. So as the water approaches a 0 level, H goes to 0, the flow rate goes to 0. So the outlet velocity at the drain is the square root of 2 times the gravitational acceleration, 9.8 meters per second squared, times the height of water in the tank. So you're given this expression for the outlet flow velocity. So we start off with a certain height of 1 meter in the tank. Pull the cork, water starts to flow out the drain to the bottom. We want to know how long it takes to drain the tank down by 90%. In other words, H2 is equal to 0.1 meters. The height, H2, the height down to 1/10 of a meter. How long does it take to drain 90% of the water volume in the tank? What is T2? Okay, so the velocity and therefore the flow rate at the outlet is going to change with time. So clearly we're going to have to do some integration here to figure out how long it takes to drain the tank. Okay? All right, so let's get started here. How long does it take to drain 90% of the water out of the tank? Here's our system or control volume. Oops. So there's our system right there. And clearly we have mass flow crossing the system boundary at the outlet. So this is the outlet here. There's no inlet. The system is composed of the H2O, the liquid H2O. So the system is shrinking. The volume of the system is shrinking over time as we drain some of the fluid out. All right? Okay, so we've defined the system as encapsulating the liquid H2O inside of the tank, and over time flow, or H2O leaves the system at the outlet at the bottom. We want to know how long it takes to drain 90% of the H2O liquid away, starting off with an initial height of 1 meter. Okay, let us apply the mass balance to this open system. We have one outlet, so clearly this is an open system. So analysis. So we have an open system. So let's write conservation of mass down for our open system. The change in mass within the control volume with respect to time is equal to the sum m dot in minus the sum m dot out. All the inlet flow minus all the outlet flows from the various inlets and outlets. Now in this case, we don't have any inlets. The control volume is that surrounding the liquid H2O in the tank. So we don't have any inlets, but we do have an outlet. No inlets, but we do have an outlet. No inlets, so this is 0, but we do have an outlet. Now the mass flow at the outlet is going to be equal to, so this is m dot out. The mass flow at the outlet is going to be equal to the density of the water. The density of the water times the flow area times the velocity at the outlet. Velocity times the flow area, that gives you a volume flow rate, times the density, and that'll give you m dot. So V dot out times the density at the outlet, and V dot out is the flow area times the velocity, VEL, at the outlet. In other words, A flow, VEL out times the density of the H2O. So rho out is the density of the H2O, okay? I guess I'm calling the area, I'm calling this A out, I guess. Keep my nomenclature the same, the outlet flow area. All right? So I have the time rate of change within my control volume of mass is equal to, and I have an outlet, so I got to carry the negative sign. I have A out, velocity out, density of the H2O. Okay? density of the H2O. Maybe I should put some assumptions here. I'm going to assume the density of the H2O is the same. It's a liquid. So I'm going to assume density is constant. This will come into importance in just a moment. So assumptions, rho H2O is constant. In other words, incompressible. So the liquid H2O doesn't change density over time. Okay, so I'll write up my first assumption there. Now, what is the mass of H2O in my control volume? Well, that's going to be equal to the volume of the tank times the density of the H2O. So V tank times density of the H2O. Density times volume gives you mass. Now the volume of the tank is going to be equal to my height h times the tank area. The tank area times the height gives me my volume for the tank. So V tank is A tank times H, and then I have rho H2O, okay? So let's write what I got here. dmCV dt is actually d vol tank, or d area tank times the height times the density of the H2O. And then I have a dt. This is mass within my tank, area tank times H times density of the H2O. That's the mass within my tank. So d A tank H rho H2O dt is equal to minus area of the outflow times the velocity of the outflow times the density of my H2O. Okay? Now, we're given the tank and the flow area. The tank and the flow area are constant, 3 square centimeters for the tank, for the outlet, and 2 square meters for the tank surface area. And we're also assuming H2O density is constant. Constant tank area, constant flow area, constant density. So because the tank and the tank area and the density of the H2O is constant, I can pull them out of the derivative. So I get A tank rho H2O dH dt is equal to area out, velocity out, rho H2O. Notice the densities cancel. So density doesn't even figure into the problem. Density doesn't even figure into the problem. And also, let's make our substitution for the outlet flow velocity at this point. VEL out is square root 2 times the gravitational constant times H. The greater the height of H2O in my tank, the greater the outlet velocity. It's not quite linear. It's to the half power for H. So let me make the substitution here. Let's see, the outlet flow velocity. We are given, this is square root 2GH. Okay? So let's write out what I have. Area tank dH dt is equal to flow area of the outlet, 2GH, and the density terms are gone. Okay? So let me solve this for dH dt. the time rate of change of height within the tank is equal to the ratio of A out over A tank, the ratio of the outlet flow through the drain, flow area through the drain, and the tank area, square root 2GH. Okay. So this is an important equation. Let's call it equation number 1. And I'm going to erase some of this stuff over here. Application of open system mass balance. So we have a differential equation there, equation 1, which gives me the rate of change of height within my tank. It's a differential equation. How do we get the amount of time it takes to drain the tank by 90%? Well, we're going to have to integrate this equation and then plug in the various H values as well as our areas and the gravitational constant. So let's integrate equation 1 from T1 to T2. So integrate 1 from T1 to T2, or if you like, H1 to H2. Okay, let's integrate. Now, one thing to do here first is I'm going to separate variables. I'm going to take the dt and put it over here, and the square root h and put it over here. So we're going to separate variables. So I'm going to rewrite equation 1. So let's rewrite equation 1, and we have the h's on the left and the t's on the right. So dh, and then I'm going to divide both sides by square root h. The square root h goes away on the right and appears on the left. So I have a out over a in, and then I have a square root 2g. And then I'm going to take the dt and put it over on the right-hand side of the equation. So I have a dt right there, okay? That can be integrated. That can be integrated from H1 to H2 and from T1 to T2. That can be integrated. By the way, T1, the initial time, I've defined T1 to be equal to 0 seconds. T1 is equal to 0. I want to know how long it takes, in other words, T2 to drain the tank by 90%. So I guess I may as well set this equal to 0 right now, okay? T1 is equal to 0. I want to know time T2, in other words, how long it takes to drain the tank by a certain amount. So let's integrate this here. Well, the antiderivative of 1 over the square root of h is 2 times the square root of h, evaluated from h1 to h2. The antiderivative of 1 over square root of h is 2 square. If we can check this, you take the derivative of the square root of h, the 1/2 pops out, the square root h goes to the denominator, and the 2 in the numerator cancels out with the 1/2 or the 2 in the denominator, and you get 1. So this looks pretty good. 2 times the square root of h. And then the areas are all constant. 2 times the gravitational constants are all constant. They can be pulled out of the integral. And I get area out over area tank, square root 2g. And then I have t evaluated from T1 equals 0 to T2. Okay? So let's plug in here. Let's plug in the limits and let's see what we got. Let's plug in the limits and we'll see what we got. We're running out of chalk here. There we go. Let's see here. 2 times square root h2 minus square root h1. Okay, plug in the limits on the left-hand side, and then I have A out over A tank square root 2g. Plugging in the limits for t here, I get t2. t1 is equal to 0, so I'm just going to let that go away. All right? So let's solve for t2. The time at state 2 as a function of various initial and final heights is, let's see here, 2 square root h2 minus square root h1. And then I've got divided by A out over the tank area. And then I got square root 2g. Now I can divide both sides by 2. Oh, I'm sorry, this is equal to t2. Okay? So the time, and we'll flip the equation in just a second, get t2 on the left-hand side. So the time t2 to drain the tank is a function of these various initial and final heights and the gravitational constant and the ratio of the flow areas. Let's get rid of this 2 here. This doesn't look good. Let me divide top and bottom by 2, and I get square root h2 minus square root h1, and then I get what? A out over A tank, and then I've got square root g over 2, gravitational constant over 2, okay? Divide top and bottom by 2. Becomes a 4, or a 1 over 4 when you pull it into the square root, and that cancels out partially with the 2 in the numerator. That's where the g over 2 comes from, okay? So let's write down the final expression here for time t2. And then we can plug in numbers and figure out exactly how long it takes to drain the tank by 90%, okay? Let's see here. So t2 equals square root h2. Oh, I forgot a negative sign. Let's see here. That would have been, remember we had a negative. I dropped the negative sign. We had a negative m dot out. So there's a negative sign floating around here. Just put it in front of, just put it right here, okay? There's the negative sign right there. Getting a little sloppy. There's my negative sign, square root h2 minus square root h1. Negative sign, okay? And then I have area out over the tank area, square root gravitational constant divided by 2. Now, we have the heights. We have the height h1, which is 1 meter. The height h2, which is 0.1 meters. Did I include that? I did not include that here. h2, 0.1 meter. So we're going to lose 90% of our volume and therefore mass. I have my h1, I have my h2. I have my outlet and my tank area, the surface area for the tank, and the flow area for the outlet flow. I've got all that. G, of course, is 9.8 meters per second squared, so I can plug that in just a moment. Okay. So we got everything. Let's plug in. Negative square root h2. Let's see, h2 is 0.1 meters. h1 is 1 meter. And then I have the ratio of area out to area in. Let's see, the outlet area is 3 centimeters squared. And the tank area is 2 square meters. The surface area of the tank. It's a cylindrical tank. Apparently, its top surface area is 2 square meters. I have some unit problems here. I need to get these areas in the same units. So there is, for every 1 meter, there is 100 centimeters, and I'm going to square that. I get centimeters squared, and that will cancel out with the centimeters squared in the numerator, denominator, numerator, and I will get meters squared in the equation, okay? And then I have my square root G over 2. So I got 9.8 meters per second squared, and then I'm going to divide that by 2. Let's crank the numbers out here and see what we get. Let's crank the numbers out. Let's see here. So we get negative. I get the numerator and I get negative 0.68, and that will have unit of square root meters. Square root meters, so that's my unit. And then I have, let's do the denominator here. So let's see here, give me a second. So 9.8 divided by 2 times 3 divided by 2 divided by 10 to the 4th. So I get 3.32 10 to the minus 4. That's the 100 squared there, so that's 10 to the minus 4. And the areas cancel out for the units, and I get square root meters per second squared. That comes from the acceleration term with the square root. Now let's look at the units here before I plug in and get the final answer here. The meter here cancels out, the square root meters cancel out in the numerator and the denominator, and I end up with 1 over square root seconds. That's going to go up in the numerator. Square root seconds will go up in the numerator, and my final unit will be seconds. So let's cancel this here. I did it again. Negative times a negative, that will be, sorry about that, that will be a positive sign. Sorry about that. Square root 1 meter is greater than square root 0.1 meters, so this quantity in brackets is going to be negative. So we get 0.68 divided by 3.32 times and I get 2,048.2 seconds. Let's just make sure that's right here. Let's see here, 0.68 divided by 3.32, yeah, times 10,000. That should be fine. So that is seconds. Let's write that in minutes here. Let's see here, divide by 60, and that gives me 34.1 minutes. Or if you want it in hours, 0.569 hours, okay? The unit conversion here, if you want to do the unit conversion, let's see here, there is 1 minute per 60 seconds, and there is 1 hour per 60 minutes here. So that's how we do the units, okay? 34 minutes to drain the tank. Let's write that down. T2, 34.1 minutes. That's my draining time. That's my draining time to drain the tank. Okay, so this is an unsteady problem. We're actually we're removing mass from a control volume, removing mass from our system. So the amount of mass is changing with respect to time in the control volume. So it's an unsteady problem. dmCV dt is not zero. So this is a cute little problem, cute little unsteady problem for you to chew over, okay? 34 minutes to drain the tank. This is a pretty complicated problem. I don't think most of your problems you're going to do are going to be this complicated, but it shows the power of conservation of mass applied to an open system, okay? Okay, so after that example involving application of the mass balance, and remember the mass balance for an open system was derived by applying the Reynolds transport theorem to conservation of mass. So after that two examples we had there for mass conservation for an open system, let's shift gears to the more important and more interesting application, which is conservation of energy for an open system. So energy balance, E-balance for an open system. So let me show you what such an open system might look like, and I'll draw and show you what possible energy interactions there might be. So we could have this weird generic system with all these inlets and outlets. So we have all these inlets and outlets. Okay, so we got mass flowing in. Maybe this is inlet port number 1. So m dot in 1. Maybe this is inlet port number 2. So we have m dot in 2, all the way down to however many inlets we have. Same thing on the outlet side. We have mass flowing out. So this is m dot out 1. M dot out 2, all these mass flows out of my system. And here's the control volume for my system. It's clearly an open system. We got mass crossing the system boundary at various locations. So that is my control volume or my system, okay? So we have all these inlet flows and all these outlet flows. Okay? Now remember from our discussion of closed systems, there are various kinds of energy interactions that occur. There's work and there's heat. So I could be adding heat to my system, Q dot. I could also be doing work on, or the system could be doing work. So I could have a propeller here with some W dot shaft going on. So this guy could be turning and delivering power at a rate of W dot shaft. I could also have some wires in here. Okay, I could have some wires in here, and that could be the positive and negative lead, and therefore I can have some W dot electric, can barely write it down there, W dot electric. And that would be work on the system, okay? Pass a current through the wire, you're doing work on the system as it's being dissipated through a resistor. Let's see, so there's shaft work, electric work, boundary work. We could have a piston in here. We could have a piston, okay? And this piston could be moving up or down. So I could actually have a piston on the boundary of my open system, and it could be moving up or it could be moving down, changing the volume of the system, and therefore doing boundary work. So I could have W dot boundary as well, okay? I could have W dot boundary. Three kinds of work: electric, shaft, and boundary work. All can be present for my open system. Okay, let's write the Reynolds transport theorem here. Now that we have an idea of what our system may entail, mass flows across the system boundary, various kinds of heat and work interactions. So the Reynolds transport theorem says what? It says the change of beta, time rate of change of beta within my closed system is equal to the time rate of change of beta within my control volume with respect to time, plus the sum of m dot lowercase beta out minus the sum of m dot lowercase beta or lowercase b in, summed over all inlets and outlets. Okay? So those are our Reynolds transport theorem. We derived that during the previous lecture, as I recall. All right? Now, in this case, if you go back and look at that chart we had a long time ago, I think it was in the last lecture, if we apply this to energy, what we're saying is beta is equal to total energy, lowercase b is equal to energy per unit mass, so that's lowercase e, and the time rate of change of energy within my closed system, d beta closed system, dt, in this case, beta is equal to total energy, dE dt, is equal to the heat added minus the work done. So you go back and you look at that table we had where I had different values for beta, and I had the closed system energy and mass balance. You'll see these terms in that table, okay? Okay, so let's plug in. The change of beta within my closed system is really the time rate of change of total energy within my closed system. And that's equal to Q dot minus W dot. So that's my closed system energy balance right up here. This is my closed system energy balance. Change of beta within the closed system. Beta is energy. So this is change in total energy within my control volume with respect to time. And lowercase b becomes energy per unit mass, so I have the sum of m dot e out, and this one becomes the sum of m dot e in. Okay, so that's what those terms become when I have the energy, when I apply it to total energy E. Apply it to total energy E. Oop, looks like my microphone cut off. I think we're going to stop. Okay, so I've replaced the batteries here. I hope you can hear me now. So again, just to review here, we have the Reynolds transport theorem applied to total energy E. In this case, beta is equal to total energy, internal plus kinetic plus potential. Lowercase b is beta per unit mass, so that's specific total energy, lowercase e. And d beta dt is actually dE dt for the closed system. And so I have my closed system rate-based energy balance on the left-hand side. Let's write out our final result here. Let's write out our intermediate result. So let's see here. So this implies, let's write down what we got. Q dot minus W dot is equal to the time rate of change of energy within my control volume, my open system, if you like, plus the sum of m dot E out minus the sum of m dot E in. Now, let's expand this energy term here. These energies here, these lowercase e's, these are the specific total energies at the various inlets and outlets. So if you look over here at inlet number 1, there's actually a E1 here, an internal energy, specific internal energy, kinetic and potential energy of inlet flow number 1. There's actually an E2 here. I guess I'm calling it EN1 and an EN2. So there are specific energies associated with all these flows across my system boundary. Let's expand what these specific energies are. So this little guy here, this is specific internal plus potential lowercase pe plus lowercase ke. And as a result, I have dE, the change in energy with respect to time inside my control volume is equal, plus sum m dot U plus PE plus KE summed over all the outlets minus the same thing summed over all the inlets. Okay? Q dot minus W dot, the heat added minus the work done by my open system is equal to the time rate of change of energy in my open system plus the sum of the total energy flows out minus the sum of my total energy flows in. U plus PE plus KE. Okay? By the way, what is this dECV dt term here? What's this? What energy am I talking about here within my control volume? Time rate of change of energy within my control volume. Well, there's actually a certain amount of energy associated with the mass in my control volume. There's a certain amount of mass in my control volume, and there's a certain amount of energy within my control volume. So the energy balance, that time rate of change of energy within the control volume, is the rate at which energy inside is going up or going down. Okay? All right, now, before we get too much further here, I want to point something out. What happens if we don't have any mass flows at all? If that system over there had no m dots, no mass crossing the system boundary. In other words, it was a closed system. Closed system has no mass crossing the system boundary. Then these m dot terms would go away. These represent energy flows across the system boundary. These guys would go away, and I would get Q dot minus W dot is equal to dE dt within the control volume. That would be the closed system energy balance. So the open system energy balance is equivalent to the closed system energy balance. It reduces to the closed system energy balance when there are no mass flows across the system boundary. We would hope that it did. We would hope that it did. Okay. Now, there's one little thing here. There's actually a new form of work that we encounter when we have open systems. A new form of work. There are actually pressures on the various inlets and outlet port locations. There's actually pressures there. So the pressure is applying a force. The flow is moving in and out of my system through the ports. So we have fluid moving. In other words, we have flow velocities. A pressure times a velocity times a flow area gives you a power. So the pressure at the inlet and the outlet ports results in work or power being applied to my system. There is a fourth form of work or power being done when we have an open system, and it's associated with pressure. We're going to call this work pressure work. It's the work required basically to force the flow in and then force the flow out. A pressure work, a fourth form of work. Remember the previous three were boundary, shaft, and electric, but now we have a fourth, which is pressure work. So let's take a moment here to investigate what pressure is, pressure work, or if you like, pressure power. Power is energy per unit time. So let's investigate what pressure power is and how we calculate it and how we can incorporate it into our energy balance. Okay, so right now, in fact, let me make sure we're on the same page. Right now, this W dot term contains actually four kinds of work or power. There's W dot shaft plus W dot electric plus W dot boundary, and now we got the new one, W dot pressure. So there's actually four kinds of work or power going on. The additional kind due to pressure to force the flow in and then out of the control volume is only present when you have an open system. Now we're going to try to calculate what this pressure power is, or pressure work per unit time, and then we're going to modify our energy balance so that it contains automatically the pressure power, okay? So, let's say we have a channel. So here's our little channel right here. We have an inlet and an outlet. Now at the inlet, I have a pressure P1, I have a velocity VEL1, and of course I have a density ρ1, and I have a flow area, area 1. So maybe this is a circular pipe, so this is area 1. Okay, maybe that's our inlet flow area. Same thing at the outlet. Same thing at the outlet. I have a P2, I have a ρ2, I have an area 2, and of course I have a velocity VEL2, okay? VEL2. Now, let's look at the work being done on the system due to the pressures at the inlet and the outlet. So net work per unit time due to pressure. So let's look at the work being done on the system due to the flow moving into the system. My system is the area in this pipe or channel. Okay, that's my system. So on the left-hand side, I have a force due to pressure. F1 or F pressure 1 times a velocity, VEL1. A force times a velocity gives me power or energy per unit time. A force times a distance is work. So force times distance divided by time gives me power. So this is pressure power on the right-hand side, left-hand side. F pressure at location 1 times the velocity at location 1. Now the pressure force is equal to pressure at the inlet, P1, times area 1. Okay? So now I have P1 area 1 times velocity VEL1. So this is equal to W dot pressure at location 1. W dot pressure at location 1. A force times the velocity gives me work per unit time. Let's do the same thing on the right. Now this is, by the way, this is on system. We're pushing the fluid in, so we're doing work on the system. Now on the right, we have flow moving out. So F press at location 2 times velocity at location 2. That gives me pressure power, and that is being done by the system. There's a pressure here, and the system is pushing the fluid out. So the system is doing work to push the fluid out. So F press 2 times velocity 2, that's equal to the pressure at the outlet times the flow area at the outlet times velocity VEL2. Okay? And that is equal to the pressure power at location 2, and that is by system. On system, by system. On system, by system. Okay, a force times the velocity applied at the inlet and the outlet gives you powers. Okay? Now I'm going to rewrite both of these equations in terms of the mass flow rate. A velocity times an area times a density. Velocity times an area gives you a volume flow rate times a density would give you a mass flow rate. So I'm actually going to write one more line here. P1, and I'm going to multiply both sides of the equation. Divide and multiply this term by density, and I'll end up with an m dot. So I have m dot 1, and then I have a 1 over density 1. So I divided and multiplied this term by density at the inlet. Area times the velocity gives me an m dot. So I get m dot 1 over density. Same thing over here. P2, m dot 2, 1 over density rho 2. Okay? One last thing, 1 over density is specific volume. So I can actually write this as P1, m dot 1, specific volume at the inlet. And I can write this as P2, m dot 2, specific volume at the outlet. Okay? So this is the important version to look at. Pressure times m dot times a specific volume gives you pressure power or work per unit time. Work per unit time. Okay, let's take what we have here and incorporate it into our energy balance. Oh, before we do that, let's ask ourselves what the net work done by the system. What's the net power or net work per unit time done by the system due to pressure? Net pressure power, W dot pressure. And what I mean by that is by system. Well, that's equal to P2 M dot 2 minus specific volume at location 2. So P2 M dot 2 specific volume at location 2 minus the work done on the system, P1 M dot 1 specific volume 1. So this is all equal. This is W dot pressure. That's the pressure power, net pressure power done by the system. Okay, by the system. Okay, let's substitute this in to our energy balance over on the right. Let's substitute that in here. Q dot minus, and then I got a bunch of works. W dot, and they're all works. I'm going to divide this work up into two specific terms. Everything that does not belong in pressure power, and then pressure power. So W dot exclude pressure power. So that's shaft electric boundary. We're pretty used to these. And then I've got minus P2 M dot 2 V2, P2 M dot 2, specific volume at location 2, minus P1 M dot 2, I'm sorry, M dot 1, specific volume at location 1. By the way, in our channel problem, we only have one inlet and one outlet. So I'm going to write dECV dt, and then I have one inlet and one outlet. So M dot 2, that's my outlet. U plus PE plus KE2 minus M dot 1, that's my inlet. U plus PE plus KE1. So I'm applying my energy balance to my channel. Apply my energy balance to the channel. One inlet, one outlet. Let's see what the energy balance looks like applied to my channel. So apply to channel. Okay. Let's take the pressure power term. So this is the pressure power term. W dot. That's my W dot pressure. Let's take it and put it on the other side of the equation. Let's move it over to the right. Q dot minus W dot. And this W dot excludes pressure, power. In other words, it's boundary plus shaft plus electric, all the stuff we're used to for a closed system. And then I got the time rate of change of energy within my channel. And then I got, okay, I'm going to take this term and put it over on the right, and I'll have an m dot P2 V2, which I can combine in this term, m dot U plus PE plus KE. So m dot 2 U plus pressure times specific volume. There is my pressure power, PE plus KE applied calculated at the outlet. So here I got my pressure power term in parentheses minus m dot 1 U plus pressure times specific volume plus specific potential energy and kinetic at the inlet. What is U plus PD? What's U plus pressure times specific volume? We know what that is. That's specific enthalpy, H. H. I told you enthalpy was going to be important soon. Enthalpy crops up when you're doing open system energy balances all over the place. Q dot minus W dot. I'm not going to write excludes pressure power anymore. It's understood that this is shaft, electric, and boundary. D ECV dt plus m dot 2 H plus PE plus KE at the outlet minus m dot at the inlet, H plus specific potential plus specific kinetic energy at the inlet. This is the open system energy balance as applied to my single inlet, single outlet channel that we use to derive the expression for pressure power. The only difference between this equation and the original energy balance we had prior to the discussion of pressure power is the internal energy was here in place of the enthalpy. So this version right here includes the effect of pressure power automatically within the energy balance. And we do that by substituting H in place of specific internal energy, U. And the W dot here, remember the W dot is W dot shaft plus W dot electric plus W dot boundary, okay? No pressure power in this term. The pressure power has been swallowed up on the right-hand side and the U's became H's. Let's write the final version of the energy balance for multiple inlets and outlets. We had a single inlet, single outlet. For the example, let's generalize this for multiple inlets and outlets. Q dot minus W dot is equal to the time rate of change of energy within our control volume plus sum m dot H, not U, PE, KE summed over all outlets minus the same thing. M dot H, not U, plus specific potential and kinetic summed over all inlets. This is the open system energy balance, including pressure work or pressure power. Open system E balance. Write it down, commit it to memory. We're going to be using this equation for the rest of the semester more or less, just like we've been using the energy balance for a closed system over the semester. We're going to continue to use it and continue to use this. Write it down. There are H's here instead of U's. Next time we will do examples. We'll spend a day or two just on open system devices and applying the energy and the mass balance to open systems. That's all for today, ladies and gentlemen. Take care.